Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up sections 1.1 and 1.2 from your textbook, which is an introduction into sort of the basic terminology and ideas behind differential equations. In the previous video, as we sort of discussed, section 1.1 we're pretty much sort of skipping over because it's more of an introduction about why we want to study differential equations, and we'll actually see a lot of those models that are mentioned in that section 1.1 later on when we move into sections officially on modeling using differential equations. And we've been focusing more of our attention on 1.2, which gave us some basic terminology, ideas, definitions behind working with differential equations. In the previous video, we investigated mostly what it actually means to be a differential equation, how to classify differential equations by their order, which of course is just the highest derivative present in the differential equation, also how to classify differential equations as linear or non-linear, and then we also spent a good amount of time just understanding what it means to be a solution to a differential equation. The first thing we're going to talk about in this video is taking that concept of a solution to a differential equation a little bit further, and we're going to define what it means to be the general solution to a differential equation. So let's take a look at this definition here. A solution to an nth order differential equation is called the general solution if the following two conditions are satisfied. So there's two conditions that must be satisfied for a solution to be counted as the general solution. First, the solution needs to contain n unknown constants. So it has to have a number of unknown constants that match its order. So these constants usually are labeled C1, C2 through Cn. Second, which is the much sort of more important part, which is really why it's given that name, the general solution, is that every solution to the differential equation can be written in this format, meaning that every solution to the differential equation can be written in the format of the thing we're claiming as the general solution. What that means, because written in this format is not a particularly mathematically precise way of defining something, what that means is that every solution to the differential equation can be found by choosing appropriate values of the constants C1, C2 through Cn. So in other words, every particular solution you can find for the differential equation can be thought of as a part of this general solution by choosing the correct C1, C2 through Cn. Now, general solutions are something that are really powerful and important in solving differential equations, because if something has a general solution, then you know the format of every possible solution to that differential equation. And a lot of the sort of theory that we develop, especially later on when we sort of return to differential equations a second time, is going to be about coming up with theory that helps us understand the format of these general solutions, how to find the general solutions, etc. But we do have a very important note that we'll talk about more as we sort of move forward and start to solve differential equations. While general solutions are really useful and very powerful if we can find them, you should be aware that not every differential equation has a general solution. So general solutions are something that we want to be able to find, but not every differential equation has a general solution. In fact, there are differential equations out there that don't have any solutions at all, let alone a general solution. So while this is something that we want to be aware of, not every differential equation that we write down actually has a general solution. If you want, you can look back at the video from the previous part, so the section 1.1 and 1.2 part 1. We actually found a solution at one point that is a general solution in that video. There was an example where we showed that y equals c root x was a solution to a differential equation. That actually turns out to be the general solution for the differential equations of that form. We don't quite know that yet because we don't know how to solve differential equations just yet, but we have seen an example of a general solution already, and we'll see another one sort of at the end of this video. So this is the first other definition that we wanted to extend. We knew already from the previous video what it meant to be just a solution to a differential equation. Now we know what it means to be the general solution. Whether or not those exist, that's a different question, or a different story altogether. All right, now we're ready to sort of talk about something that relates this concept of solutions and general solutions and puts this together with some initial conditions. And that's what's called an initial value problem for a differential equation. So an nth order differential equation on an interval I that is given n initial conditions of the form y at x0 is some constant z sub 0, y prime at that same x sub 0 is z sub 1, all the way down to the n minus first derivative at that same x sub 0 is equal to z sub n minus 1. So these are all just constants here. where that x sub 0 is, of course, in the interval that everything is defined on. This is what's called an initial value problem. So an initial value problem is basically an nth order differential equation along with these n initial conditions. Keep in mind that this is an n initial conditions because we're going from the function to the n minus first derivative. So this is sort of 1, 2, down to n different conditions, even though it's based on the n minus first derivative. What does it mean to solve an initial value problem? Well, solving an initial value problem means that if you find a solution to an IVP, which is often how we abbreviate, there we go, I lost the word there for it. If you want to abbreviate or sort of have just some initials for an initial value problem, an IVP, the solution to an IVP is a function or a relation that is both a solution to the corresponding differential equation, so you have to solve the differential equation, of course, and you have to satisfy all of the initial conditions. So when you solve an IVP, you're not only solving the differential equation, but you're also making sure that the function has all these properties here. So to get a little bit of a handle on this definition here, let's go ahead and do another example of determining if something is a solution. This time we're going to determine if the function y equals x squared plus 2 is a solution to the given IVP. So we have this IVP here that says y triple prime plus y equals x squared plus 4. And the initial conditions are y at 1 is supposed to be 3, y prime at 1 is supposed to be 2, and y double prime at 1 is also supposed to be 2. Notice that this is a well-defined IVP here, because if we just sort of note off to the side, this guy is third order. Since this is third order, it's third order because we have a third derivative in there. To be an initial value problem, we have to give conditions on the function, its first derivative, and its second derivative, because we have to go to the n minus first derivative in terms of the initial conditions. You guys should also be able to see that this guy would be a third order linear differential equation because the triple prime and the y, the dependent variables, are in separate terms, no functions of those, so it is indeed linear. So we need to determine if this function is a solution to this IVP. So we've got two things we need to do. We need to make sure that it solves the differential equation, and we need to make sure it satisfies the initial conditions. Checking the initial conditions should be easier, so let's start with that. So we have y equals x squared plus 2. We can also just get all the derivatives that we're going to need. Y prime is going to be 2x. Y double prime is going to be 2. And then technically to plug into the differential equation, we're going to need to know the third derivative, and that's going to be 0. So let's check the initial conditions. So check initial conditions. So y of 1 is going to be 1 squared plus 2, which is indeed 3. Check. Y prime at 1 is going to be 2 times 1, which is indeed 2. Check. And y double prime at 1, well, there's no x to plug into, so it's always just 2. Check. So our claimed solution, x squared plus 2, does indeed satisfy all the initial conditions. Does that mean it's a solution to the IVP? Not at all, right? It just means that it solves the initial conditions. Now we need to make sure that this also solves the differential equation. So now we check the differential equation. This is where we want to use that left-hand side, right-hand side approach. So the left-hand side is y triple prime plus y, and of course the right-hand side is just x squared plus 4. So let's plug in, right? Y triple prime is supposed to be 0. So we get we get 0 plus, and y is x squared plus 2. So we get x squared plus 2, and of course we have x squared plus 4 here. And here we get x squared plus 2. Over here we get x squared plus 4. So what we can see here then is that unfortunately this left-hand side does not always equal to this. Does not always equal this right-hand side. It doesn't ever equal it, because if you try to solve x squared plus 2 equals x squared plus 4, you'll never get any solution. Doesn't matter though, it's not always true, right? So the left-hand side does not equal the right-hand side for all x. So this is not a solution to the IVP. So while the given equation here did go ahead and actually satisfy the initial conditions, it had all the right properties, it failed to solve the differential equation, so it is not a solution to the IVP. To be a solution to the IVP, all these things would have to check out, and the differential equation itself would need to check out as well. So that just wanted to give you guys one example of checking whether or not something is a solution to an IVP. It's very, very similar to checking if it's a solution to the differential equation. Just got that extra step as well. Do keep in mind, I would strongly recommend that you go ahead and you use the approach that I did here, where you check the initial conditions first, because checking the initial conditions should be much easier, and if that one fails, we could have skipped all this work entirely. In this case, this one passed, and then we had to do the slightly harder one, and that one failed, so it still failed overall, but it's not a bad idea to always just start with the initial conditions. All right, let's go ahead and move on then. So the next thing we want to talk about is something that sort of ties together a lot of the concepts we've already been talking about, and it's a really, really important theorem. It's called the existence and uniqueness theorem for linear differential equations. Existence and uniqueness theorems, which we often abbreviate as E plus U theorems, are absolutely essential for differential equations. Unfortunately, these types of theorems are very, very challenging to prove, and the two major existence and uniqueness theorems that we talk about in this class, unfortunately, we have to state without proof. The vast majority of theorems in this class that we encounter, we will prove, but these existence and uniqueness theorems, even though they're very, very important, they're just beyond the scope of our class to actually prove directly. So let's see what this existence and uniqueness theorem says. So this existence and uniqueness theorem applies to linear differential equations, so it only applies to linear ones. So we're going to suppose that you have an nth order linear differential equation of this form. Notice that we've already put it into standard form, so the nth derivative of y plus a1x n minus 1 derivatives of y plus an minus 1 of x y prime plus anxy equals some function f of x. And we're going to have the additional assumption that a1 all the way through an of x, along with that capital F of x, are all continuous on some interval. Then, any IVP for this differential equation with conditions of this format, right? So again, the IVP, since this is nth order, has to have those n conditions, starting from a condition on the function to a condition on the n minus first derivative of the function. And as long as that x sub 0 is inside of that interval, is guaranteed to have a unique solution. Now, this is an incredibly powerful and important theorem because it's guaranteeing two things, even though it only says we'll have a unique solution. By saying will have, that guarantees that a solution exists. And by saying unique solution, that means that there's only one solution. So in other words, the way that you can sort of say this informally is that for nth order linear differential equations, every IVP has unique solutions. So notice that when we're talking about unique solutions, that's a concept that really only makes sense once you talk about an IVP. That idea of uniqueness applies when you're talking about IVPs because IVPs have those initial conditions that you need to satisfy. All right. So why is this theorem so important? And I mean, does it matter that we know that these IVPs have unique solutions? Well, even though the concept of a general solution isn't mentioned in here, it actually turns out that this theorem allows us to prove things are actually general solutions. So we're going to wrap up this introduction by proving something is a general solution. And before we get into this proof, I do want to just tell you guys, this is sort of a very unique would be a bad pun, I guess, bizarre idea here because we still don't know how to solve anything. We're just saying if somebody told us that this is a general solution, we now would know how to prove that it's a general solution. We're not actually finding out how to find these solutions yet. That's for later on in our class, but we're just going to prove that something is a general solution if somebody gives it to us ahead of time. So let's go ahead and take a look at that. So for this example, we're going to prove that the general solution to this differential equation, y double prime minus y equals 0, is y equals c1 e to the x plus c2 e to the minus x. So we want to try to prove that this is the general solution to this. So how are we going to do this proof? Well, the first thing we need to do is we need to prove that this actually is a solution. Forget about it being a general solution. We need to prove that it is a solution. So first thing we need to do is we need to show that y equals c1 e to the x plus c2 e to the negative x is a solution to y double prime minus y. Forget about it being the general solution. We just need to make sure that it works. So how do we do that? Well, now we can do our left-hand side, right-hand side. So we'll need to know the second derivative. So we have c1 e to the x plus c2 e to the negative x. I guess that tells us that y prime is c1 e to the x minus c2 e to the negative x. And then y double prime is going to be c1 e to the x plus c2 e to the negative x, because we're using chain rule on those components there. So now we can do our left-hand side, right-hand side approach. So the left-hand side is y double prime minus y, and the right-hand side is, of course, just 0. So let's plug in. For y double prime, we get c1 e to the x minus c2 e to the negative x. And then we are subtracting the y, which is c1 e to the x plus c2 e to the negative x. And I'm sorry, this should be a plus there because we're talking about y double prime right here. So this guy right there. All right, and of course the right-hand side, nothing really to do there. It's just 0. Well, here we can just distribute that negative sign, and we can see that those are going to cancel, those are going to cancel, and yep, indeed, we get 0 and 0. So the left-hand side always equals the right-hand side for all x. So we just figured out y equals c1 e to the x plus c2 e to the negative x is a solution to y double prime minus y equals 0. Okay, so we definitely know that this is a solution. Now we need to try to prove that it's a general solution. So let's talk about that on the next page here. So, how to prove it's the general solution. Well, let's go back and take a look at the definition of a general solution. So, a general solution we gave here had these two conditions. First, the solution has to contain n unknown constants, where n matches the order. So in our case, that's nice and easy, right? We're talking about a second-order differential equation, and notice that our solution does have two unknown constants. So we're all good with that, right? So for condition 1 needs to contain two unknown constants. Okay, check. That's nice and easy. What about condition 2? Well, condition 2 is a little bit more complicated. It says that every solution can be written in this format. So we need to somehow prove that. So it turns out that there's a nice trick and something we're going to see many times to sort of do this. So what we're going to do is we're going to let f of x be a solution to y double prime minus y equals 0. So we're going to let some function, right? Maybe we should phrase it this way just to make things a little bit easier. Let's let y equal f of x be a solution to this. So in other words, we're going to pick out something else that is a solution. What we need to show then is we need to show that y equals f of x can be written as y equals c1 e to the x plus c2 e to the negative x. In other words, we're saying if we pick out any solution to this thing, then it can be written in this format. And if we do that, then that'll prove that it is a general solution, because we're saying that every solution to this differential equation comes in this format. So how do we do that? Well, it turns out that this is very hard to do just directly, but we can make use of our existence and uniqueness theorem. This thing here is certainly a linear differential equation. So let's just note y double prime minus y equals 0 is a linear second-order differential equation. So let's consider the IVP y double prime minus y equals 0 with the initial conditions that y at 0 is f of 0 and y prime at 0 is f prime at 0. Now, for this IVP, you'll notice that automatically, just by the way I sort of made this up, right? I'm saying that y at 0 is supposed to be f of 0 and y prime at 0 is supposed to be f prime of 0. That means this y equals f of x, which we know is a solution to the differential equation, so it solves that, will certainly also satisfy those initial conditions, because what is f of x at 0? It's f of 0. What's f prime at 0? It's f prime at 0. That's sort of dumb, right? We're making up an IVP that is guaranteed to be solved by this. So we know y equals f of x solves this IVP. We know that. In fact, that's why I chose this IVP, to make sure that it's an IVP that this y equals f of x is going to solve. But let's see if we can figure out some choices of constants for C1 and C2 to also solve this, right? So let's see if we can do that. But let's consider, right? But consider y equals C1 e to the x plus C2 e to the negative x. With y prime, then of course being C1 e to the x minus C2 e to the negative x. Notice that y at 0 here would be C1 plus C2, and y prime at 0 would be C1 minus C2. But we want these to be equal to f of 0 and f prime of 0. So we get a little sort of weird system of equations. We say C1 plus C2 is supposed to be f of 0, and C1 minus C2 is supposed to be f prime at 0. But you guys can solve this for the constants. That's not hard to do. Let's go ahead and just add the equations together. If you do that, you should get like 2C1 is f of 0 plus f prime at 0. So C1 should be f of 0 plus f prime of 0 over 2. And if you pop that back in, you get f of 0 plus f prime 0 over 2 plus C2 is supposed to be f of 0. Subtract that over and it looks like C2, you can just think about this as like 1/2 and 1/2. So it looks like C2 should be f of 0 minus f prime at 0 over 2. So what does this tell us? Well, we know that something of this format will solve the differential equations, and if we choose the constants like this, it'll also satisfy the initial conditions. So what we've just figured out is y equals f of 0 plus f prime at 0 over 2 e to the x minus f prime 0 minus f prime at 0 over 2 e to the negative x will also solve the IVP. Okay, so we found two solutions to the IVP. But this is where the theorem comes in. The theorem that we just talked about, this existence and uniqueness theorem, says that if you have a linear nth order differential equation and you have an IVP for it, it has a unique solution. It only is supposed to have one solution. So, since it's only supposed to have one solution, what does that tell us? Well, that tells us that this y equals f of x must be the same as this. So what this tells us is, this tells us by existence and uniqueness theorem that f of x must be equal to this f of 0 plus f prime at 0 over 2 e to the x minus f at 0 minus f prime at 0 over 2 e to the negative x, which tells us that no matter what f of x is, remember we just said f of x is some arbitrary solution, it can always be written in this format where C1 is this choice of constant and C2, oh, sorry, this should be a plus here, right, because it's just plus C2, and where C2 is this constant. So in other words, we're saying that every solution can be written in this format where we do C1 e to the x plus C2 e to the negative x. So every solution is of this format. So y equals C1 e to the x plus C2 e to the negative x is the general solution. Check. All right. Now, this is, I mean, for the start of a class, this is a pretty bold sort of proof to just launch into. So I want to just quickly recap some of the key features of this. So the main idea here is that we initially started by just taking the thing that somebody claimed was the general solution and showing that it was a solution. This is exactly where what we were doing from the first video. Very simple to see that things of this form certainly satisfy this differential equation. What's trickier is that to be the general solution, you have to make sure that any solution fits this format. So what we did is we took an arbitrary solution. We just said, let y equal f of x be any solution to this. Who knows what it looks like? It's just some solution to this. Our goal then was to say that if this guy is a solution to this, then this guy is actually of this format. Well, to do that, we made up an IVP. And we made that IVP be an IVP that we knew y equals f of x had to solve. In other words, we made the initial conditions based on f of x. We said y of 0 is f of 0, y prime at 0 is f prime of 0. It doesn't matter that we pick 0 in there. We just use that for ease because evaluating things at 0 is nice and simple. But we made sure that y at 0 was f at 0, so that this guy would work, and y prime at 0 was f prime at 0, making sure this guy worked. So we immediately knew then that y equals f of x solved this IVP. But then we went through this sort of brute force moment here where we said, okay, let's use this format and figure out what C1 and C2 should be to solve this IVP. We found out that C1 should be this f of 0 plus f prime of 0 over 2, and C2 should be f of 0 minus f prime of 0 over 2. So we then knew that this will also solve the IVP. So at this point, we sort of realized that we had y equals f of x solve the IVP, and this crazy thing solve the IVP. Then the big theoretical thing, the whole mechanism that drives this thing forward, is that existence and uniqueness theorem. The existence and uniqueness theorem says that since it's an IVP, and since it's a linear differential equation, there can only be one solution. In other words, this solution here, right, this y equals f of x, and this guy here must be the same thing. So f of x had to be of this format, so every solution, every arbitrary solution must be of this format. That's what it means to be a general solution. This is a very sort of bizarre proof, but we will see things similar to this as we move forward in our class. This is a very common way of showing that something is a general solution. And general solutions are going to be something we're on the lookout for very frequently in the class. So we will see other things that sort of have a similar structure to this. For now, though, this is going to wrap up sections 1.1 and 1.2. In the next video, we'll be moving into section 1.3, looking at another existence and uniqueness theorem, and thinking a little bit about visual ways to understand solutions to differential equations.